Right. So we said most things want to have that filled octet. Of course, there's exceptions. We've already taken a look at one of them in hydrogen, where it only wants two electrons, but of course there are other exceptions as well. So one exception is if you have an odd number of electrons. So for example, NO, this is nitrogen monoxide. It's a molecule that exists in real life, right? So our model has to somehow reflect that. And if we think about nitrogen monoxide, nitrogen has 5 valence electrons, oxygen has 6 for a total of 11. And so then we draw our Lewis structure, NO, right? There's nothing that goes in the center because there's only 2 of them there. We draw a single bond between the two. That'll use up 2 electrons. We're down to 9. Then we start giving things octets, starting with the more electronegative atom. In that case, that's oxygen. So that right there uses up 6 down to 3. And then we'll just give the remaining 3 to this nitrogen. The nitrogen is still short of an octet. So what we can do is we can move one of these lone pairs from oxygens to form a double bond. And then if we think about where our nitrogen is at, it has 2, 3, 4, 5, 6, 7 valence electrons here. We don't want to form a triple bond because then we'll have more than 8 valence electrons, and that's a big no-no for nitrogen. So we just have to stop here, right? We've got an odd number. There's no way you can make it an even number. This is simply an exception to our Lewis structures. Overall, this is a pretty reactive molecule. So while it does exist in real life, it's pretty reactive. And part of why it's reactive is because that nitrogen doesn't have a filled octet. But just something to keep in mind. Another exception is boron and aluminum. They only want 6 valence electrons, right? Everything else wants 8 valence electrons. Boron and aluminum just decide, nope, we're not going to do that. We're only going to have 6 valence electrons. So for example, BH3, that's a very common molecule. Boron has 3 electrons. Each hydrogen has 1. There's 3 of them. Go ahead, sum them up. That's 6 valence electrons. Hydrogen is terminal, so boron goes into the center. And then we do 1, 2, 3 bonds. That uses up all of our valence electrons. And in this case, boron only has 3 bonds, and it's totally happy like that. Same thing with AlH3, pretty much the exact same thing. Aluminum has 3 valence electrons. Hydrogen has 1. There's 3 of them. Draw the Lewis structure, right? Al, 3 H's. Doesn't matter if you put 2 H's on the bottom, 1 on the top. It's either way, it's fine. Form the bonds. Use up all of our electrons. Aluminum is perfectly fine with only 3 bonds or 6 valence electrons. And then finally, the last exception is expanded octets. So some atoms or some elements are indeed able to break the octet rule. They can have more than 8 valence electrons. We're just gonna mention them here, but you'll learn more about them in Chem 101. We're just gonna stick with things that stay with our 8 valence electrons. But just to give you an example, like SF6, that one, in this one, the sulfur has more than 8 valence electrons. If you think about it here, it has 12 valence electrons. And of course, each one of these fluorines has all of these dots. As you can tell, you don't need to be an artist to know chemistry, but it probably would help. So just some exceptions to keep an eye out for. The main one that I want you to know is this boron and aluminum, that they only want 6 valence electrons.